Right now, beneath your feet, Earth is destroying evidence of its own past. Tectonic plates grind ancient seafloor into molten rock. Rain dissolves mountains that once touched the sky. Rivers carry away the remnants of lost civilizations. Every day, our planet systematically erases chapters from its history, wiping clean the geological record with processes so relentless that most of Earth's 4.5 billion year story is simply gone. We've lost entire eons of time, whole worlds of ancient life, forgotten continents and vanished oceans. The evidence was destroyed by the very planet it recorded. This isn't careless destruction. It's built into the fundamental mechanics of how our world works. And the implications are staggering, because if Earth erases its own history, what else might be hidden forever beneath the surface or lost to processes we barely understand? Hit that like button and subscribe as we explore the greatest archive destruction in history. Prepare yourselves. We begin. Imagine trying to write the history of humanity, but 90% of all documents, artifacts, and records have been systematically destroyed, not lost in wars or accidents, but erased by the fundamental processes that keep civilization running. That's the situation geologists face when studying Earth's history. The planet constantly recycles itself, destroying old rocks to make new ones, burying evidence under sediment, grinding up the geological record, and reconstituting it in different forms. The oldest rocks we've found on Earth are only 4.4 billion years old, and they're tiny zircon crystals, nearly indestructible minerals that survived when the rocks containing them were destroyed and recycled. The oldest actual intact rock formations are around 4 billion years old, found in remote regions of Canada and Greenland. This means we've lost at least 500 million years of Earth's early history. The first 500 million years of our planet's existence left almost no trace. This lost period, called the Hadean Eon, was crucial for Earth development. During this time, the planet was bombarded by asteroids and comets. The Moon formed from debris when a Mars-sized object collided with early Earth. The surface was likely molten or partially molten for millions of years. Somehow, this hellish world cooled enough for liquid water to exist, and possibly for life to begin. We know almost nothing about this period, because Earth destroyed the evidence. Why does Earth erase its history? The answer lies in plate tectonics, the process that makes our planet geologically active and probably essential for life, but also the mechanism that systematically destroys old crust. Earth's surface is divided into tectonic plates, massive slabs of crust floating on the semi-molten mantle beneath. These plates move, driven by convection currents in the mantle, as hot material rises and cool material sinks. When plates collide, one is often forced beneath the other, in a process called subduction. The descending plate is pushed deep into the mantle where extreme temperature and pressure melt it back into magma. This process is happening right now at subduction zones around the Pacific Ring of Fire, along the western coast of South America, beneath Japan, and in dozens of other locations. Every year, square kilometers of seafloor disappear into the mantle, carrying with them the geological record preserved in those rocks. The seafloor is Earth's newest crust, constantly being created at mid-ocean ridges where magma wells up and forms new rock. But this new seafloor has a limited lifespan. As it moves away from the ridge where it formed, it travels across the ocean basin until eventually it reaches a subduction zone and plunges back into the mantle. The oldest seafloor still existing on Earth is only about 200 million years old, found in the Mediterranean Sea and parts of the Atlantic. This means we've lost over 95% of all seafloor that ever existed. The oceans cover 70% of Earth's surface, and their entire geological record older than 200 million years is gone, vanished into the mantle, melted and recycled. Any evidence of ancient marine life, extinct ecosystems, past ocean chemistry, climate records, all erased by subduction. Continental crust survives longer than oceanic crust because it's less dense and more buoyant, resisting subduction. When continents collide with oceanic plates, the denser ocean floor gets subducted while the continent rides over it. This is why we have ancient continental rocks, but no ancient seafloor. Continents are the survivors, the fragments that escape destruction, while ocean basins are constantly renewed. But even continental crust isn't permanent. Erosion gradually wears down mountains and continents, carrying sediment to the oceans where it accumulates on the seafloor. That seafloor eventually gets subducted, and the sediment is dragged down into the mantle or scraped off and incorporated into mountain ranges. Over hundreds of millions of years, entire mountain ranges can be eroded flat. The Appalachian Mountains were once as tall as the Himalayas, but have been worn down over 300 million years. This erosion destroys the geological record in a different way than subduction. Instead of melting rocks, it breaks them into smaller pieces, transports them to new locations, and buries them under younger sediment. The evidence still exists physically, but it's scrambled and hidden. A rock that formed in an ancient mountain range might end up as sand grains on a beach thousands of kilometers away, mixed with sand from dozens of other sources, making it nearly impossible to reconstruct the original rock's history. The rate of erosion depends on many factors, but on average, continents lose about 1 meter of elevation every 10,000 years. This might sound slow, but over geological timescales, it's devastating. A mountain, range 5 kilometers high, will be eroded to sea level in 50 million years if nothing uplifts it. Considering Earth is 4.5 billion years old, mountains much older than a few 100 million years are extremely rare. Most ancient highlands have been completely leveled. Water is the primary agent of erosion. Rain falls, dissolves minerals in rocks, and carries them away in streams and rivers. The chemical weathering of rocks by slightly acidic rainwater breaks down minerals and releases ions that eventually reach the ocean. Physical weathering occurs when water freezes in rock cracks, expanding and splitting the rock apart. Rivers transport billions of tons of sediment every year from continents to oceans. The Ganges and Brahmaputra rivers alone carry over 1 billion tons of sediment annually, from the Himalayas to the Bay of Bengal. The Mississippi River transports over 500 million tons per year to the Gulf of Mexico. This sediment was once solid rock in mountains and highlands. It represents the gradual destruction of continental crust, the wearing away of the geological record grain by grain. Wind also contributes to erosion, particularly in dry regions. Dust storms in deserts lift fine particles and transport them across continents and oceans. Sand dunes migrate, burying and uncovering landscapes. Over millions of years, wind can erode substantial amounts of rock, creating dramatic landscapes like the sandstone formations in the American Southwest. Ice is perhaps the most powerful erosional agent. Glaciers are like giant bulldozers, scraping up everything in their path as they flow downhill. During ice ages, continental glaciers covered large portions of North America and Eurasia, grinding down the landscape and eroding enormous quantities of rock. The Great Lakes were carved by glacial erosion during the last ice age. The fjords of Norway and New Zealand are drowned glacial valleys. evidence of ice's power to reshape continents. But erosion isn't just about physical removal of rock. Chemical weathering alters the composition of rocks, transforming them into different minerals and often destroying the original structure. Limestone dissolves in acidic water, creating caves and karst landscapes, but also destroying fossils and geological features. Granite weathers into clay, completely changing its texture and composition. The information encoded in the original rock, its mineral composition, crystal structure, chemical signature, is lost as weathering transforms it. This chemical alteration is accelerated by life. Plant roots grow into cracks, physically breaking rocks apart. Acids from decaying organic matter enhance chemical weathering. Bacteria and fungi can dissolve minerals to extract nutrients. Life speeds up erosion and weathering by orders of magnitude compared to purely physical and chemical processes. In a strange irony, life helps destroy the evidence of past life preserved in rocks. The burial of rocks under sediment creates another form of erasure. When sediment accumulates in basins, it buries older rocks beneath kilometers of younger material. The weight of overlying sediment increases pressure and temperature in the buried rocks, often altering them through metamorphism. Sedimentary rocks can be transformed into metamorphic rocks, destroying their original features, fossils, and textures. Under extreme pressure and temperature deep in the crust, rocks can partially melt, producing magma that eventually crystallizes as igneous rock. This completes the rock cycle, turning sedimentary or metamorphic rock back into igneous rock and erasing all information about its previous forms. A granite that crystallizes from magma might contain atoms that were once part of an ancient fossil, but all trace of that fossil's structure and identity is gone, melted and reconstituted into new minerals. The rock cycle ensures that Earth's crust is constantly being recycled. Igneous rocks weather and erode into sediment. Sediment compacts into sedimentary rock. Sedimentary rock gets buried and metamorphosed into metamorphic rock. Metamorphic rock melts into magma that crystallizes as igneous rock, completing the cycle. At each stage, information is lost or transformed, making it increasingly difficult to trace the history backward. This recycling is why Earth's surface is relatively young compared to the planet's age. The Moon, which lacks plate tectonics and has minimal erosion due to no atmosphere or water, preserves craters and rocks over 4 billion years old across much of its surface. Mars similarly retains ancient crust, with regions dating back 4 billion years. Earth's geological activity erases evidence that other rocky planets preserve. The implications for the fossil record are profound. We've found fossils spanning the past 540 million years in remarkable detail and diversity. But this represents only the most recent 12% of Earth's history. The Precambrian, comprising the first 4 billion years, has a sparse and fragmentary fossil record. We've found evidence of microbial life dating back 3.5 billion years, and chemical signatures suggesting life might have existed 3.8 billion years ago. But the diversity and evolution of early life remain mysterious, because most of the rocks that could have preserved fossils have been destroyed. The Cambrian explosion, when complex multicellular life diversified rapidly about 540 million years ago, might seem sudden partly because the earlier record is so poor. Perhaps complex life had been evolving for hundreds of millions of years before the Cambrian, but we've lost most of the evidence. The apparent explosion might be partly an artifact of preservation, with Cambrian and later rocks surviving in much greater abundance than older rocks. We know that animals with soft bodies existed in the Ediacaran period, just before the Cambrian. Strange frond-like organisms, quilted creatures, and early animals left impressions in rocks from about 570 to 540 million years ago. But how long had these lineages been evolving before we first see them? We don't know, because older rocks are rare and often heavily metamorphosed, destroying any fossils they might have contained. The loss of the early fossil record means we can't directly observe how life originated. We have no fossils from the Hadean or early Archean, showing the transition from non-living chemistry to living cells. The earliest clear evidence of life is from 3.5 billion years ago, by which time cells were already sophisticated enough to form stromatolites, layered structures built by microbial communities. The origin of life itself happened earlier, during the period for which we have almost no rock record. The pre-Cambrian fossil record that does exist is biased toward shallow marine environments where sediment could bury organisms before they decayed, and where those sediments weren't later destroyed by metamorphism or erosion. Entire ecosystems that existed in deep oceans, on land, or in environments that didn't preserve well might have left no trace. We're seeing a filtered sample of ancient life, the portion that happened to fossilize in rocks that happened to survive to the present. This preservation bias affects even the relatively recent fossil record. Terrestrial vertebrates are much rarer as fossils than marine invertebrates, because land environments tend not to preserve remains as effectively. Forests and grasslands erode rather than accumulate sediment. Carcasses decay in open air. Only organisms that died in rivers, lakes, or coastal areas where sediment could rapidly bury them had good chances of fossilization. We're missing most of the terrestrial ecosystems that existed throughout Earth's history. The fossil record is also biased toward organisms with hard parts. Shells, bones, and teeth fossilize much more readily than soft tissue. This is why the Cambrian explosion seems so dramatic. It coincides with the evolution of mineralized skeletons, which preserve well. Soft-bodied organisms existed before and after the Cambrian, but they rarely fossilize. The Burgess Shale, a famous Cambrian fossil site in Canada, preserves soft-bodied organisms due to exceptional conditions, revealing a diversity of life forms that wouldn't normally fossilize. How many other soft-bodied ecosystems have vanished without a trace? Even for well-studied periods like the Mesozoic era, when dinosaurs dominated, we've probably found only a small fraction of the species that existed. Paleontologists estimate we've discovered perhaps 5 to 10% of all dinosaur species, and those discoveries are biased toward large animals from environments that preserved well. Small dinosaurs, terrestrial ecosystems between fossil sites, and entire lineages that happen to live in regions where rocks didn't preserve are largely unknown. The geographic distribution of fossil sites is uneven. Some regions have abundant sedimentary rocks from certain time periods, while other regions have none. North America and Europe are exceptionally well studied because they have many paleontologists and good outcrop exposure. Vast regions of Africa, Asia, and South America remain poorly explored. Fossils exist in these areas, but haven't been found yet because no one has looked carefully. The known fossil record is shaped by where paleontologists happen to work, not just by what was preserved. Plate tectonics compounds this problem by moving continents around over geological time. Fossils from ancient equatorial regions might now be in polar areas. Rocks formed on one continent might be incorporated into a different continent through collision and amalgamation. The paleogeography, the ancient configuration of continents and oceans, was completely different in the past. Reconstructing where ancient organisms lived requires understanding plate movements, which themselves are inferred from the very rocks that plate tectonics has deformed and altered. Beyond fossils, we've lost other types of historical information. Climate records preserved in rocks are incomplete. Ice cores from Antarctica and Greenland provide detailed climate history for the past 800,000 years. But ice older than that has been destroyed by glacial flow, carrying it toward the edges where it melts. Ocean sediment cores extend the climate record back millions of years, but only from the past 200 million years because older seafloor has been subducted. Climate history older than a few million years must be inferred from indirect proxies like isotope ratios in rocks, which can be altered by metamorphism. We've lost most evidence of Earth's magnetic field history. The magnetic field has reversed hundreds of times, with north and south magnetic poles switching. These reversals are recorded in rocks as they form, with magnetic minerals aligning to the field direction at the time. But metamorphism and alteration can reset this magnetic signature. For much of Earth's history, we have only fragmentary magnetic field records, making it difficult to understand how the field has behaved over billions of years. Impact craters, evidence of asteroid and comet collisions, are gradually erased by erosion and plate tectonics. The Moon and Mars are covered with craters from billions of years of impacts. Earth experienced similar bombardment, but most impact craters have been destroyed. We've identified only about 200 impact structures on Earth, almost all younger than 2 billion years. The craters from the heavy bombardment period 4 billion years ago are completely gone. We know this bombardment happened because we see it recorded on other bodies in the solar system, but Earth has erased its own impact history. The late heavy bombardment, a period about 4 billion years ago when the inner solar system experienced intense asteroid impacts, might have repeatedly sterilized Earth's surface or alternatively delivered the organic compounds needed for life. We don't know, because the rocks that would tell us have been destroyed. This is one of the most important events in Earth's history, potentially determining whether life could establish itself, and we've lost the direct evidence. Even relatively recent history is incomplete. The ice ages of the Pleistocene, occurring over the past 2.6 million years, involved multiple advances and retreats of continental glaciers. Each glacial advance eroded away much of the evidence left by previous glaciations. We have good records of the most recent glacial cycle, which ended about 12,000 years ago, but earlier glacial cycles are poorly known. Each new glaciation partially erases the record of those before it. Human prehistory faces similar limitations. Archaeological evidence is destroyed by natural processes. Organic materials decay, leaving only stone tools and occasionally bones. Wooden structures, leather clothing, plant fiber textiles, most of the material culture of prehistoric humans, decays completely within thousands of years under most conditions. We have stone tools going back millions of years because stone is durable, but this gives us a biased view of ancient technology. Entire civilizations might have existed and left no trace. If a sophisticated culture existed in regions where erosion is rapid, or where their structures were built from organic materials, very little might survive to be discovered. This is not to suggest ancient advanced technological civilizations existed without evidence, but it highlights how much information can be lost. Even known ancient civilizations reveal themselves incompletely. We have monumental architecture from ancient Egypt, but know little about the daily lives of common people, whose houses were built from mud, brick that eroded away. The rate of information loss accelerates in the past. For recent history, we have abundant evidence. Medieval and Roman remains are well preserved in many locations. Going back thousands of years, evidence becomes sparser. Going back millions of years, the record is fragmentary. Going back billions of years, we have only the tiniest scraps of information. This creates a deep uncertainty about Earth's early history. The further back we look, the less we know, and the more speculative our reconstructions become. Some entire chapters of Earth's history might be completely unknown. There could have been ecosystems, environmental conditions, or even brief warm periods during snowball Earth episodes that left no trace because the rocks that would have recorded them were destroyed. We can infer that such things might have existed through indirect reasoning, but we cannot know for certain. Snowball Earth episodes, when the entire planet might have frozen over about 700 million and 2.3 billion years ago, are themselves known from fragmentary evidence. The rocks suggesting global glaciation are rare and often controversial. Did Earth really freeze completely? Or were there refuges of liquid water? How did life survive? We don't have enough preserved rock from these periods to answer definitively. The evidence was erased by subsequent geological activity. The Great Unconformity, a gap in the rock record between about 700 to 500 million years ago in many locations, represents a period when extensive erosion removed large volumes of rock. This erosion might have been enhanced by the breakup of the supercontinent Rodinia and by glaciations during snowball Earth events. Whatever the cause, enormous amounts of geological and paleontological information were destroyed. Entire chapters of life's evolution during this period are lost. Similar unconformities, gaps in the rock record representing periods of erosion or non-deposition, appear throughout geological history. Each unconformity represents lost time, missing pages in Earth's history book. Some unconformities span millions or tens of millions of years. The information about what happened during these gaps is gone forever, unless we find locations where deposition continued and rocks were preserved. The destruction of Earth's history isn't just about rocks and fossils. It affects our understanding of planetary processes. We'd like to know how plate tectonics started, but the evidence was destroyed billions of years ago. Did Earth always have plate tectonics, or did this process begin at some point after the planet formed? The oldest preserved oceanic crust is too young to answer this. The oldest continental rocks show signs of having been involved in plate tectonic processes, but we can't be certain about earlier periods. We'd like to know when Earth's magnetic field originated. The magnetic field shields us from solar wind and cosmic radiation, and might be essential for life. But the early magnetic field history is poorly constrained because suitable rocks are rare. We have some magnetic measurements from rocks 3.5 billion years old, suggesting the field existed by then, but we don't know if it existed earlier or how strong it was. We'd like to know the composition of Earth's early atmosphere and oceans. Chemical and isotopic proxies provide clues, but the information is incomplete and sometimes contradictory. The atmosphere has changed dramatically over geological time, from lacking oxygen to having 21% oxygen today. This transition happened between about 2.4 billion and 500 million years ago, during the Great Oxidation Event and subsequent oxygenation periods. But the details are murky because we've lost most of the rocks that would tell us exactly how and when oxygen increased. The rise of oxygen is one of the most important events in Earth's history, enabling the evolution of complex, multicellular life. But we understand it poorly because so much evidence has been destroyed. We can see the consequences, the appearance of oxidized minerals, and the eventual evolution of animals, but the causes and mechanisms remain debated. Was it biological evolution producing more oxygen? Changes in ocean chemistry sequestering oxygen sinks? Tectonic changes affecting volcanic gas emissions? We don't know for certain. Even the question of how life originated is affected by the destruction of evidence. The conditions on early Earth, the chemistry of the early ocean and atmosphere, the availability of energy sources, all are poorly constrained because we've lost the rocks from the Hadean and early Archean. Laboratory experiments attempting to recreate the origin of life must make assumptions about conditions, and we can't verify those assumptions against geological evidence because the evidence is gone. Some scientists propose that life originated multiple times, with early forms being repeatedly extinguished by asteroid impacts during the late heavy bombardment, until finally a resilient lineage established itself and persisted. We cannot test this hypothesis because we have no rocks from that period preserving evidence of life or its absence. The timing of life's origin is constrained only by the age of the oldest fossils we've found, but life could have originated earlier during the period for which we have no record. The destruction of Earth's history also affects astrobiology. If we want to understand how planets evolve and whether life is common, Earth is our primary example. But Earth is a planet that actively erases its history, making it difficult to study its own past. This is problematic for understanding planetary evolution in general. Mars and the Moon preserve ancient surfaces that tell us about conditions billions of years ago. Earth doesn't, despite being the planet we'd most like to understand. When we search for life, on Mars or on exoplanets, we need to understand what biosignatures to look for. Earth's history should inform this search, but gaps in the record limit what we can learn. We don't know what Earth looked like from space 3 billion years ago. Would we recognize it as inhabited if we observed it with telescopes? The atmosphere composition, surface chemistry, and spectral signatures of ancient Earth are uncertain because we've lost so much geological and geochemical data. The erasure of history is built into how Earth works. Plate tectonics drives subduction, which destroys crust. Plate tectonics also drives mountain building, which leads to erosion. The water cycle moves water from oceans to atmosphere to land and back, enabling erosion and sediment transport. All these processes are essential for Earth's habitability. They regulate climate, recycle nutrients, and create diverse environments. But they also destroy the geological record. This creates a profound tension. The processes that make Earth suitable for life also erase the evidence of past life. Plate tectonics might be necessary for complex life because it regulates atmospheric carbon dioxide through the carbonate-silicate cycle, preventing runaway greenhouse effects or icehouse states. But this same plate tectonics destroys most of the crust within a few 100 million years through subduction. Could a planet preserve its history better while still being habitable? Perhaps a planet without plate tectonics, but with some other temperature regulation mechanism, could maintain old surfaces like Mars does while remaining habitable. But we don't know of any such mechanisms. On Earth, at least, habitability seems to require the very processes that erase history. This has implications for how we should think about the Fermi paradox. If we're looking for evidence of ancient civilizations or past life in the solar system, we need to remember that planetary processes erase evidence over millions of years. Even if life existed on Mars billions of years ago, finding evidence might be extremely difficult if Mars had more erosion or tectonic activity in the past. The absence of evidence isn't strong evidence of absence when planets destroy their own history. On Earth, we've developed methods to extract information from the limited record that remains. Isotope geochemistry can reveal temperatures, atmospheric compositions, and biological activity from tiny rock samples, molecular fossils, chemical signatures of ancient organisms persist in some rocks even when physical fossils are absent. Detrital zircons, tiny crystals that survive the destruction of their parent rocks, carry information about ancient crust that no longer exists. These techniques allow us to push back into the Hadean, despite lacking intact rocks from that period. Zircons, as old as 4.4 billion years, contain oxygen isotope ratios, suggesting liquid water existed on Earth's surface. This is remarkable evidence from nearly the beginning of Earth's history, preserved in crystals smaller than sand grains, while all the surrounding rock was destroyed and recycled. Geologists have also learned to read highly deformed and metamorphosed rocks, extracting information from rocks that have been altered almost beyond recognition. Sophisticated laboratory techniques can identify mineral assemblages, indicating the original rock type and conditions of formation, even after intense metamorphism. This allows reconstruction of ancient environments from rocks that superficially appear to have been completely reset. But there are limits to what can be recovered. Some information is destroyed permanently. Once a rock melts completely, its structure and much of its chemistry is reset. Once fossils are metamorphosed beyond recognition, we cannot reconstruct what organisms they came from. Once an ancient landscape is eroded flat, we cannot fully determine what it looked like. We can extract more information as techniques improve, but we cannot recover what has been destroyed completely. The ongoing destruction continues today. Right now, subduction zones are consuming sea floor that contains sediments and fossils from the Jurassic period, erasing evidence of ecosystems from nearly 200 million years ago. Rivers are carrying sediment from the Himalayas and Andes to ocean basins, destroying mountain rocks that formed tens of millions of years ago. Erosion is wearing down ancient cratons, the stable cores of continents, removing billion-year-old surfaces grain by grain. Future geologists, if they exist millions of years from now, will face the same challenges we do. They'll have abundant information about their recent past, but will struggle to understand the deep history of their planet. Our current era, the Quaternary period, will eventually be represented by only scattered rock outcrops, with most evidence erased by future tectonic and erosional processes. The fossils of today's species will be rare finds in the distant future, and much of 21st century Earth will be unknowable to far future science. This destruction is neither good nor bad. It's simply how planets work. Earth is a dynamic system, constantly recycling and renewing itself. This dynamism is probably essential for maintaining habitability over billions of years, but it comes at the cost of erasing history. The planet we inhabit has forgotten most of its own past, destroyed the evidence through the same processes that keep it alive. The implications are humbling. We're piecing together Earth's history from fragmentary evidence, filling vast gaps with inference and speculation. For much of the past 4.5 billion years, we have only educated guesses about what happened. The actual history is lost, destroyed by the relentless mechanisms of our active planet. We'll never know most of what happened during the Hadean. We'll never recover the complete fossil record of the Precambrian. We'll never see what most of Earth's ancient landscapes looked like. But what we have discovered is extraordinary. Despite the destruction, we've reconstructed the broad outlines of Earth's history. We know the planet formed 4.54 billion years ago. We know life emerged at least 3.5 billion years ago. We know about mass extinctions, ice ages, continental drift, the rise of oxygen, the evolution of complex life. We've learned this from the small fraction of rocks that survived, and from the clever techniques scientists developed to read those rocks. The story of Earth is a story of impermanence. Mountains rise and erode. Oceans open and close. Continents merge and split. Species evolve and go extinct. And through it all, the planet erases the evidence, destroying the record of its own transformations. Earth doesn't preserve its history like a museum. It's more like a palimpsest, a manuscript that's been written, erased, and rewritten countless times, with only fragments of earlier texts showing through. We exist at a moment in this ongoing process, able to look back through the fragmentary record and glimpse something of what came before. But we see through a glass darkly, with vast periods unknown and unknowable. The planet beneath us is ancient beyond comprehension, yet most of its story is lost. Earth erases its own history as a consequence of being alive, being active, being the dynamic world that made life possible. And in doing so, it ensures that its deepest secrets remain forever hidden, buried beneath the weight of time and the relentless renewal of the surface we call home.